Hey everybody, this is 8.3. This is exponential functions. So we've done compositions, we've done inverses, and now we're moving into sort of the meat of this chapter, which starts with exponential functions. Basically, an exponential function is a function with an exponent. So if b is any real number such that b is greater than 0 and not equal to 1, for any number x, a function is of the form f of x equals b of x, b to the x is an exponential function, okay? So this set of functions in this section are going to have exponents. First, this is practice in your calculator. You're going to approximate what the expression is. You round the answer that you get here to 4 decimal places. So in this case, you have to be able to figure out what 8 to the power of radical 3 is in your calculator. See if you can figure out what keys you have to push in which order to get that. If you need help, you should drop into chat. The answer here should be somewhere in the neighborhood of 36.66. That's the estimate. So it should be, in most of your calculators, it's 8 and the caret key, and then 3 square root, okay? Try this one, 5 to the power of negative square root of 17, okay? That one should come out to be 0.0013. You really need to make sure that you take the time to do this on the calculator, because when it comes to test time and final exam time, these will be the problems you get to blow right through and are easy wins. But if you don't know how to use the calculator or what keys to place, these become a huge problem and you can't figure them out any other way. So you have to be able to do this. Please take the moment to do it. All right, try the square root of 10 to the square root of 2. That one should come out to be around 5.0946. This is a good conversation to have with your partner too. Make sure you both can do this. All right, 9 to the power of pi should be somewhere about 995.0416. 15 to the power of radical 5 should be somewhere in the neighborhood of 426.4028. And square root of 7 to the square root of 3 comes out somewhere in the neighborhood of 5.3936. So far, so good. Look at us go. All right, so this is our first exponential function. It's 2 to the power of x. It asks us just to start by graphing it, just so we can get a sense of what exponential functions look like. So let's do that. So if I'm going to make my little xy chart here, 2 to the negative 2 would mean flip. It would be 1 over 2 squared, which would be 1 over 4. So this is going to be 1/4. 2 to the negative 1 would be 1 over 2, right? Anything to the 0 power is not 0. Anything to the 0 power is 1 every single time, okay? 2 squared is 2, and 2 to the second power is 4. So we have our little chart. Let's make our little graph. Let's see. And how high do I need to go? All right, so when x is negative 2, y is way down, it's like a fraction, right? So it's way down here. When x is negative 1, it's a half, it's creeping up. At 0, it's 1. At 1, it's 2. At 2, it's 4. So these look like a curve this way, okay? Notice these are one-to-one functions. That's because they're functions, okay? So that's the first graph. Let's try this one, though. This is 1/2 to the x. So this is just slightly different than what we just did, but we're going to make the same kind of chart. So if we do 1/2 to the negative 2, well, that flips the fraction. That makes it 2 squared. That's 4. 1/2 to the negative 1 flips it and makes it just 2 to the first, so 2. Anything to the 0 power is 1. 1/2 to the first is just 1/2. 1/2 squared is just 1 squared over 2 squared is a 4th. So you can see the numbers are really familiar here because we just saw them, but they're in a different order. All right, we still have 0 and 1, right? That point. But at 1, it's a half. At 2, it's a quarter. At -1, it's 2. And at -2, it's 4. This graph just goes in the opposite direction, okay? You can try to graph these two. They do something very similar. Try them out, okay? Essentially, what happens when we graph an exponential function is this is what they look like, okay? They come this way or they come this way. These are some of the properties. If b is greater than 1, so if this is a whole number b, not just a whole number, but a whole number, like not a half, right? It's an increasing exponential function. That's exponential growth. So growth this way. Okay, think about the way bacteria grow, or a culture of something in science class. They double and they double and they double and they double and they double. That's exponential growth. Okay, if b is between 0 and 1, if it's a fractional part, it's an exponential decay. This is how radioactive things decay. It's all kinds of things decline in an exponential function. The domain is always the set of real numbers, so the x values goes from negative infinity to infinity. The range is always from 0 up. So what happens is the closer the graph gets to 0, it gets closer and closer and closer and closer and closer on the y-line. It never really touches, okay? There is something called a horizontal asymptote at the line y equals 0. It means nothing goes below it. And it always passes through the point 0, 1, because f of 0, no matter what exponential function you have, anything to the 0 power is 1 every time. All right, so we're going to use this to do stuff. In a sample originally composed of 1 gram of radium-226, which is radioactive, the amount of radium-226 present after T years is given by this formula. A of T equals half to the power of T divided by 1,620. A is the amount of radium in grams, and T is the time. How much radium will there be after 1,620 years? Well, this is a time, right? We know where time goes, so we just have to get an amount. We want the amount at half to the power of 620 divided by 1620. Well, half to the power of 1 is just half. So if I started with 1 gram, then half of 1 gram is just half a gram. That's how much I'm going to have, okay? In the sample composed, same question, how much radium will be present after 3,240 years? Well, we're going to do the same thing. A of T equals half to the power of 3240 divided by 1620. All right, we'll divide those two. You're going to find out that 3420 divided by 1620 is 2. So 1/2 squared is just a quarter. Okay, so how much is left after 3,400 years? 3,240 years? 1/4 of a gram, because 1/4 of 1 is a quarter. All right. What happens after 4,860 years? Well, we do the same thing again, right? A of T is half to the 4,860 over 1620. When you do that, you're going to find it divides to 3. Okay, so 1/2 to the 3rd power is an 1/8. So 1/8 of that original gram is left over. And no matter how long I wait, I'm never going to have it totally gone. It's the fraction of what's left is just going to get smaller and smaller and smaller and smaller. Okay, these work very similarly. Try them out. Come into the discussion if you're stuck. All right, exponential functions, whenever we talk about population growth, these are exponential functions. Radioactive decay, population, particularly it's often people, but it can be bacteria, whatever it is you're populating. So when we do population growth, you have to suppose the initial value of the population at the sum point, with the beginning of time, whatever the time is p of 0. And then population increases by a certain rate over a certain period of time. The amount of people after that time is given by p of 0, the population at whatever the starting time was, times the quantity 1 plus the rate, all to the power of time, okay? So when we do this, Okay, sorry, getting my pages in order. What happens is this. So we have a population of the Bahamas. In 2008, there were 321,000 people that lived there with an annual rate of 1.39%. We want a model that relates the population to the function of years since 2008. So what we start with is this idea that we just need a number sentence, basically. So we want P of t equals the number, the population at time 0, right? So the first population I have when time started, that's when our time is going to start because we want it since 2008 is 321,000. Okay. Then I have to do 1 plus, it's always that standard 1 because you're taking that population as you have it and growing it. The 1 gives you the initial population plus the rate. We always write the rate as a decimal. Okay, it's in a percent right now, which means you have to move the decimal to the left 2 places. So 0.0139 all to the power of time. That's our function. Okay, at the first year, it's 2008. It's the difference in the years. Sorry, I'm trying to write my numbers while I'm talking. It's not going well. It would be 2008 minus 2008. So it's at 0 years. The population at that point is just what it is, right? All right, so let's use that. The annual rate is what it was. Let's use our model to find the population in 2016, round to the nearest 1,000. So what happens is we take our model, P of t equals 321,000 times 1 plus 0.0139 all to the power of 2016 minus 2008, the difference. So that's going to come out to be an 8. Now you use your calculator. So you do what's in parentheses first, 1 plus the decimal, 0.0139 to the 8th power, and then multiply that to 321,000. That's going to get you a population probably of 358,000. Good heavens, my numbers today. All right. This works exactly the same way. You are going to try to do the same. So when we do the model, we're going to do population over time equals the initial population, which is 3,700,000, times 1 plus the rate as a decimal, 0.022%, to the power of time, in this case, which is whatever the new time is minus 2,000. Okay? When we get that, the population in 2016 in Colorado was 5,079,000, give or take. We rounded to the nearest 1,000, okay, because we don't have estimates of half people. That doesn't do us any good. All right, this is the end of exponential functions. I will see you in the next section.